field. So our speakers today are Manuela Gerato and Chris Allstott. I'll just give a very brief bio so we can get to their talk. So Manuela is an associate professor in the Department of Environmental Science and Policy Management at UC Berkeley. Chris is a researcher and data scientist in the Department of Geosciences at the University of Oslo. And they've both done a lot of work in this area. So we're excited to hear their talk today, where they're going to give us a little bit of background on what snow data assimilation is for those of you who maybe aren't as familiar, and then give us some applications. So without further ado, why don't we get started? So Manuela, if you want, go ahead and share your slides and we'll get started. For the purposes of questions, I think the organization here is each speaker will speak for about 25 minutes, leaving about 10 minutes of time for questions at the end. So I'd say let's just save questions for the end, which then there should be time and we can spend time on that. So again, thank you both, Chris and Manuela, for speaking today. Why don't we get started?
Sure. Thank you for the introduction. So as Steve said, we'll talk a little bit about data assimilation. But before getting started, my job is also to provide very basic background and concept about data assimilation. And then we'll talk about some applications, both from my side and Chris's side. So let's get started. So before actually talking about data assimilation, the framework that I want to bring data assimilation in is with respect to uncertainties. So you might have seen this graphic that shows, well, a map of the globe where the blue areas are snow, areas that are upstreams of high water needs. But I think what I would like to point your attention to is this time series graphic. So this left side graphic shows a time series of what snow water equivalent estimates will look like for the Western United States if you were to use reputable sources in order to estimate them. And then as a comparison, it also indicates the range of variability of these estimates that are about 4 times as large as the Lake Mead, which is the largest man-made reservoirs in the United States. So this is for the Western United States, an area where we think we know quite well what's happening in our mountains because we do have a lot of data. When we look into, or at least more than other side in the words, when we look into areas like, for example, in the high mountain Asia, the situation is even more dramatic in terms of the spread of the uncertainty. So large uncertainties when we estimate snow water equivalent. So why do we have these many uncertainties? Well, a lot of the estimates that we make when it comes down to making estimates spatially and temporally continuous, they could come from models. And we all know that models are great because, again, they can provide that continuity in the space and time estimation of snow water equivalent, but at the same time, they're far from being perfect. Mountains are complex environment, so parameterizing a model in order to be able to understand these physical processes can be very challenging. And then on top of that, again, the inputs that we put into these models can also be challenging to have in an accurate form. So challenges both in terms of inputs, so the forcings that we put into the place, and many of you might argue the precipitation might be the key forcing that can lead to errors in estimating snow water equivalent, but also parameterization of these models. So another way that we can actually estimate snow is, again, with observations, and I'll focus a lot on satellite observations in this talk. Before getting started, again, all of you might be aware that at this date, we don't really have yet a snow water equivalent dedicated missions. But we made quite a bit progress, I think, in the past 3-4 decades estimating snow. So first of all, for example, we can estimate snow, say, using visible near-infrared observations. So observations that can come, say, from Landsat or MODIS, that can tell us really whether we have snow covered on the ground or not. So for example, this little graphic shows an area for the Alps. So you see that you have, snow covered in the Alps, but these observations can be also affected again by clouds. But most importantly, it really just tells you whether you have snow covered on the ground or not necessarily that amount of snow water equivalent that we need for, say, hydrological purposes. If we do want to have more of a mass type of observations, we need to rely to other observations. And one very successful, perhaps, a set of observations is based on LiDAR type of remote-centric technique that is based both, say, on airborne or satellite, so airborne like the AESO, airborne, what is it called, snow observatory, or satellite, for example, like ISAT type of observations. Like for airborne, for example, these flights tend to fly, say, 1 to 4 times per season on selected watersheds. They're great because they provide meter scales observation of snow depth. Again, not necessarily snow water equivalent, but we can retrieve that using, say, models of snow depth. Other type of observations that you might be familiar with to get really to that depth or snow water equivalent can be passive microwave. So these are all great because they provide, in a way, global picture of the snow water equivalent globally, but their coarse spatial resolution tend to be not as successful for when we have to understand the processes, say, over mountainous regions. So the last, I want to say, 10 years or so, have dedicated this, the community has dedicated a lot of time and effort on understanding whether snow can actually be derived from active microwave type of sensors. So I'm thinking about Sentinel-1, as you see, for example, a graphic, a map showing products of this Sentinel-1 snow retrieval from Levens et al. 2019. This is from Sentinel-1 C-band, but also similar concept can be applied to other active microwave regions like L-band for the nicer emission and ROSE-L. So they really are based on concepts of either understanding how much the amplitude of the signal that come back, both in a backscatter type of way or forward backscatter, or looking into phase change of that signal that comes back to the sensor. So these are great because they are all weather type of observations, but because they are sensitive to many things, not just snow, they can have interferences related to vegetation, liquid water content, also even radio frequencies due to communication satellites. So in this presentation, in the context of data assimilation, I'll be focusing on assimilation of these two type of observation. So both observation from the visible infrared type of sensors and the active microwave type of world with the C-band Sentinel-1 observations. So all of this to say that also observations alone can't really provide that accurate estimates of snow that we need for our mountains. So this is why I argue that one way really to overcome those pitfalls that come from the satellite observation worlds and the modeling world comes from data assimilation. So, and this schematic is trying to convey this concept. So the idea is that, say that we do have a phenomenon of interest, and in our case, that will be, we want to understand how much snow we have in the mountains. And this phenomenon, we can both observe it. Again, we can observe it with satellite observation, but observations can be also, say, from airborne or in situ observations. And say that we can also model it with our land surface or snow models. The idea of data assimilation is to combine these two data streams, and not only these data streams, but also the uncertainties that these two data streams have to bring to the table in a Bayesian estimator type of context in order to be able to make optimal estimates of this variable of interest and also uncertainties associated with this variable of interest. In more maybe statistical term, what this is doing is effectively providing an estimate of what the prior state, again, in our case, that alpha might be snow water equivalent, but you can think about this as snowfall, snow depth, or another variable. So a prior estimate of what the distribution of that variable should look like, say through the modeling. And then when the observation is available, we compute what we call a likelihood, or like a conditional probability of what the variable of interest, so my snow water equivalent, should look like, provided that we have that observation Z. So before, again, getting to talk a little bit about application, I just wanted to give a very brief review of jargons that we might use in when we talk about data simulation. So you might have heard terms like smoothing or filtering, for example. So when we talk about, for example, a smoothing type of data simulation technique, we are talking about a data simulation that is trying to characterize, say, snow water equivalent over a past window. So using, for example, all of the measurements that are available in the window. So in this very schematic here, this shows over time observations in red dots. The smoothing type of data simulation might look something like this dark blue line, where you have a nice smoothed version of the variable that you're looking into estimating. So again, in our case, no water equivalent. And this technique you might have heard about ensemble camera smoother or particle batch smoother that are probably the most used ones, say, for snow applications. And then on the other side, we have filtering approaches. So filtering is a sequential type of data simulation where we effectively try to estimate observations as they come available in order to provide somewhat of a real-time estimate of the variable of interest. So again, in this little schematic, these can be represented by these green lines where you go from, say, one observation to another through a model. This could be your snow model or your land surface model. And as an observation becomes available at this specific time step, you adjust your model in order to, in a way, better match your observation. And in this particular case, you'll see how the model really start from that observation, because it's possible that this is more of a direct insertion type of assimilation, but in a more probabilistic sense, data assimilation really likes to apply their concept in an uncertainty in a probabilistic manner. So using also errors and uncertainties of the observations as well. So you might have heard about techniques like Kalman filters or particle filters. And with that, I also would like to also provide a very brief clarification of when we talk about Kalman versus particle, what are really referring to in very simplistic words. And hopefully that will clarify a little bit these two names as well. So when we talk about Kalman type of approaches, what we do, we track the snow state, again, snow water equivalent, via an ensemble. And then we compute mean and standard deviation to fully explain the most likely state. So we say, well, the mean of these ensamples are going to be the most likely snow water equivalent that I get. And the uncertainty can be represented by standard deviation. So because of that, by definition, therefore, these type of methods, so Kalman methods, are best used when we know that we have linear model and the errors are Gaussian, which is almost never the case for our snow and land surface models, hydrological models. But they're still very successful. The particle type of work, instead of making assumptions around whether we have linear models or whether we have Gaussian distribution of the errors, we really just draw particles from a given distribution that, again, can be Gaussian, but it doesn't necessarily need to be Gaussian. We assign some weights. In this case, for example, you see that the size of these particles are all the same. So these particles, they have all the same weights. The model run, and when an observation, this YT, becomes available, we compute the likelihood of each of these particles. So you see how, for example, the particles that are closer to in space or in time to this observation, they get more probable in a way, they get more likelihood. And then from there, if we do a filtering type of approach, we resample, so we give more probability to these particles, and then we move forward. So effectively, we are not computing mean and standard deviation from the ensemble themselves, but the snow water equivalent estimate is used from the weights of these particles that move forward in time. So hopefully this is somewhat clear from this little graphic. So with that, that concludes in a way the part that talks a little bit about background and concept. And now we can focus a little bit more on practical aspect of data assimilation, and also two really main applications that have been successful to estimate snow water equivalent. And first of all, I'll talk about a reanalysis concept, and that will be using those visible near-infrared observation of fractional snow cover area. So this is a technique that is based on a somewhat quite robust framework, the snow water equivalent reconstruction or reanalysis, you might have heard of that, that really tries to say, or really tries to recognize the fact that, yes, visible near-infrared observation, so those snow cover area observation, doesn't really provide anything about the snow water equivalent amount. But if you look into the temporal sequence of how the snow cover area depletes over time, so this is, for example, a watersheds in a small watershed in the Sierra Nevada that was part of my thesis as I was a PhD student with Steve. You see that how quickly, for example, the snow cover area depletes over time, over the melt season, might have something to tell us about how much snow was present in the first place. So if you think about, if you have a very ephemeral snowpack, it might be very quick to melt snow, say from 100% to 0%. Or another way maybe to represent this concept is shown in this time series where you have, say, over the course of the water year, the characteristic shape of what the snow cover area should look like. So again, over winter time, that is approximately 100%. And then as the summer comes into play, you start depleting the snow cover area. So the slope of this abletion curve in the snow cover area can be thought as a proportional amount of the melt that goes into place for the specific season. And this is again something that we first developed in the Sierra Nevada. Works very well because during the ablation season we don't tend to have clouds, so we tend to have a very good signal of that snow depletion curve over the spring and summer season. So ultimately, in order to get to your snow water equivalent before melt, you just sum up all of the various melt events. So this is the concept of that. And now we apply that in a data assimilation sense, where we say, well, we can have a model that is modeling both prior estimates of snow water equivalent and snow cover area. We assimilate snow cover area depletion, so not a single observation, but the entire window of snow cover areas in order to be able to capture that slope on the ablation. And the data assimilation should be able to tell me something about what's the given, what's the conditional probability of that snow water equivalent, provided the fact that I tell you what the snow cover area was like during the melt season. So this is something that we can done, of course, in a smoothing type of approach because it's happening in the past. And this is very important point. And again, this is maybe another technical aspect that I want to bring out. And so one of the first time that someone has ever assimilated snow covered area in an hydrological model with the scope to estimate snow water equivalent, tried to attempt this with a filtering type of approach. And this was the work by Costas in 2006. And they were successful, but only when they noticed that the snowpack was in a way shallow or ephemeral. And this is in a way obvious if you think about, because you're trying to estimate snow water equivalent from a snow cover area in a sequential mode. So you're really relying on the instantaneous relationship between snow cover area and snow water equivalent. And during, say, the winter months, you're having basically saturation in your snow cover area, but you still have a lot of variability of snow water equivalent. So that assimilation was really not good for deep snow water equivalent. And this is different instead when we use a smoothing type of approaches. And again, this is an example that uses a smoothing type of approaches from one of Steve's earlier paper, where we look into time series, again, in the top of snow cover area and snow water equivalent for one site in the Sierra Nevada, for which we have pillow and courses observation. And sorry that I'm not labeling this correctly, but the pillows and courses are represented by courses sites, these triangles, and the pillows are these little crosses in the snow water equivalent time series. So what we are doing in this type of smoothing type of assimilation, we are assimilating snow cover area observations. In this case, this was Landsat, and these circles are those Landsat snow cover area observations. The prior snow cover area time series is represented in red. So you'll see the median in red, dark red, and then the envelope represents the interquartile range, so an uncertainty around that value. And when we assimilate this snow cover area, not surprisingly, the data assimilation, which is the blue line, tends to agree much more with the those observation of snow cover area. So this is not surprising. I'm assimilating snow cover area, so the estimate of the model snow cover area tends to agree better with that observation. But what is nice about this technique, when you look into the snow water equivalent spectrum, and we are not assimilating any snow water equivalent observation, you see that you go from a red prior to assimilation estimate of snow water equivalent to a blue that matches much more nicely with those independent observations from snow pillows and snow courses. So this is really a key aspect when we look at data assimilation approaches for snow cover area to apply more of a smoothing type of approach. Then you can rely on that full ablation season rather than the instantaneous relationship between snow cover area and snow water equivalent. So again, this technique has been proven useful for deeper snowpack. So this was of course first developed at UCLA for the Sierra Nevada areas, but has since been deployed, I want to say, for other mountainous regions in the world, specifically the high mountain Asia and the Andes regions in South America. And yes, I might be biased, but I think this is still the state of the art snow water equivalent data sets that one can use for reanalysis purposes. So again, one can say yes, but these are still analysis of the past. What about real time? So this is why I think a lot of the attention also in the data simulation community has been focused a little bit more in the past couple of years in assimilating these active microwave type of satellite observations that can provide more of that spatial continuous in a way to estimate snow water equivalent and also in a real-time manner because they directly observe something that is telling me about the depth of the snowpack. So some examples of this data simulation technique, and this is just focused on Sentinel-1. Assimilations are reported in this highlight title. So these are recent studies that used Sentinel-1, and they are specifically estimating snow water equivalent and snow depth. So the reminder of my talk, I will present a slightly different approach that I led a couple of years ago that is still using Sentinel-1 for an assimilation approach. But in this case, we are trying to estimate precipitation amount. So the key hypothesis of the method is like, well, I'm having a snow model, and I know that in my hypothesis, the errors are primarily coming from orographic precipitation. So the overall idea is, can we use these Sentinel-1 observations, say of snow depth, available globally, to infer what the precipitation of snow should look like. So again, the idea is that can we use a bottom ground up type of approach where we say, okay, snow depth can tell us a accumulation of snow over time. Can we look into whether those observations can tell us something about precipitation? And if so, maybe we can infer something about repeatability of these precipitation patterns for, say, a real-time type of application in a hydrological sense. So this is effectively what this technique is trying to do. So if you were to just apply a very simple mass balance equation, you probably will agree with me, snow depth is proportional to snow water equivalent, and snow water equivalent can be written as, again, water balance equation, precipitation minus C minus melt. And in this case, I decided to multiply the precipitation by this alpha. This alpha is a correction factor. So the error that we multiply precipitation with in order to estimate snow water equivalent. So again, in the data assimilation sense, we come up with a prior estimate of what the alpha should look like, and then we assimilate the snow depth from Sentinel-1 in order to better retrieve that precipitation factor in a modeling type of sense. So we applied this technique in a test watershed. This is in the northern Italian Alps through some collaboration that I had with the University of Trento. We use a very simple model, SNO 17, and an hydrological model, high mod, to derive stream flow. We had some in situ observations for verification, including stream flow and snow depth observation. And we use this for 3 different precipitation products that some of you might think, oh, these are the state-of-the-art precipitation that I use for my hydrological model, something that is more atmospheric reanalysis driven, so ER5, more satellite-based, iMerge, and a Kriging version of in situ observations. You probably start seeing that they are completely different. So precipitation is a critical variable to get right in mountainous regions in the world, and this is an example of that. So here I show a result of that technique where you see for each of these precipitation data sets, so in situ observation on the top, ER5 in the middle, and then the satellite-driven iMerge observation. And this map shows what that snowfall correction factor will look like for the test years that we use this data simulation for. So the first thing that you might notice is that there is a relationship between these factors and elevation. Again, not surprisingly, low elevation tends to reduce those snowfall amounts, and higher elevation increases those snowfall amounts. But then one thing that we noticed that was kind of nice is, again, we only have 4 years, so we can't really say this in a robust manner, but there seems to be an intervenal consistency around this snowfall correction factor. So something that can tell us that perhaps this consistency can be used, say, for real-time estimation application. So this is kind of like the final results from this type of technique. We also tested this for stream flow. So one thing that maybe I'll just focus on this in situ observation type of validation. So you have stream flow on the top. Again, observations of stream flow are the black dots, the prior estimate from the model in red, and then the assimilation in blue. We noticed that we did then therefore improve a lot by stream flow, especially during the summer months, because effectively the technique is redistributing snowfall across the domain and therefore leading to releases of snow melt that was in a way better distributed in order to reach the outlet of the domain. So with that, I like to conclude my part 1, and I think I'm quite on time. And by saying that hopefully I convince you that data assimilation can be a way to overcome those pitfalls that come from satellite observations and models. And hopefully I convinced you that the data assimilation of snow cover area depletion, again in a smoothing type of sense, can provide accurate estimate of snow water equivalent, again in a reanalysis context. And that the assimilation of Sentinel-1 snow depth observation can also be seen as a sort of ground-up approach to correct those solid precipitation observations. Next direction, hopefully Chris will talk a little bit about that, but also would be to apply a little bit more some of these sequential type of data simulation in some of these exciting new active microwave remote sensing that we are having this recent years. Thank you.
Great. Thank you, Manuela. So if you do have questions, maybe add them to the chat and then we'll circle back to them at the end. So Chris, please go ahead and share your screen.
Can you see this?
Yes. Yes.
Great. Okay. I can't see you, so you have to interrupt me if something fails. So thanks a lot, Manuela, for setting this stage. Saves me a lot of time having to explain a lot of the details. So I'll dive more into applications in the context of this system that we've built together with Esteban Alonso Gonzalez at IP and also a PhD student, Marco Mazzolini here in Oslo, called MUSA, or the Multiple Snow Data Assimilation System. And the motivation for this, as Manuela also alluded to, we don't really have any really good global SWE products. Actually, the state of the art is Era 5 land, arguably, and then there's also some passive microwave, but that doesn't work in the mountains. Just like Manuela, I'm very convinced that snow reanalysis is the best approach that we have, just because of how difficult it is to infer SWE directly from remote sensing. So we need to use data assimilation. And there have been a lot of efforts pioneered by Steve and Manuela before, and now other groups too, to work and develop these methods further. We're not quite there yet to be able to do this globally. I've been trying to do that, but it's remains quite challenging because it's very expensive computationally. So yeah, but what I want to emphasize is that, at least for me, a very helpful way to think about data assimilation and why it's helpful is to think about it as a kind of inverse problem. So you imagine you have a snow model. Here I've denoted that as G, which is able to generate something like the observations that you get from your satellite retrievals. And then this snow model is a function of some hidden state variables and parameters. And then you also account for the error in the observations. And it turns out that a really nice way to solve these kind of inverse problems is with Bayes' rule or Bayesian inference. And that's what this Fox is thinking about. I think the consensus in the snow data assimilation literature is that this is the way we should do this. And I put some nice review papers there that you can look at. And this is not just an idea people have in snow science. Like there's entire fields dedicated to this. There's data assimilation, there's state space modeling, and then there's machine learning. And here I link to a kind of crash course if you want to learn more about Bayesian inference. I don't have time to give a crash course now, so don't worry, I won't do that. A little bit about the history of this MUSA system that we've developed together with Esteban. So this all started when we met as visitors at NCAR in 2018. We were PhD students back then, and we realized that there was a need for an open source data assimilation toolbox. And building on a previous literature on snow data assimilation, as well as our own research, we developed this Python package. And Esteban actually wrote the majority of the code, and I was more like a statistical consultant on the Bayesian part of things. And the seminal publication is this 2022 paper in GMD. And don't worry, I won't read all the text for you. I just put it here, and I'll share the slides at the end if anyone wants references. And then Marco also joined the development as part of his PhD, working on ISAT snow data assimilation. And recently, there's been a rising usage of this package also by other groups. And I encourage you at the end of this, if any of this sounds interesting, you're welcome to join us in developing this tool. And if you do use it, the only thing we ask is that you please cite the original paper. And there's the link to the GitHub repo as well. So the way I've structured this is using this idea of muses. So the muses, they were this goddesses of arts and sciences in Greek antiquity. And the reason I picked this framing is that musa means muse in Spanish. So it's maybe a bit of a stretch. So I've split this into 5 parts, and we'll see how much time there actually is. But the first thing I want to start with is this thing called multiplicity. I've given them fancy names to reflect that they're supposed to be goddesses, but these are real words apparently. And the first one is about how this system allows you to use multiple schemes, assimilate multiple observations, and more recently also use multiple snow models. And then, yeah, the next one that I'll talk about is the spatio-temporal snow data assimilation. And then there's been some recent work on improving particle methods that Manuela talked about by making them adaptive. I'll try to explain what that means. And then finally, we've been working on what's called hierarchical Bayesian data assimilation and how this can help to improve some of the challenges we have in snow data assimilation. And I'll end with a kind of outlook. So first, the first part is multiplicity. This is actually just introducing the MUSA framework. So in this framework, we have particle filters and particle smoothers, ensemble Kalman filters and ensemble Kalman smoothers, as well as something called iterative ensemble Kalman filters and smoothers. And more recently, we have iterative particle methods, as well as Markov chain Monte Carlo. Don't worry if none of that means anything to you, just to tell you what is there. And we're able to assimilate different types of observations, such as snow depth, fractional snow covered area, land surface temperature, also snow water equivalent, albedo, and turbulent fluxes. But the last ones there, I don't think anyone has really worked on much yet. And then the main system is built on the flexible snow model, or FSM2, which is the default model. That's the intermediate complexity snow model. But we also have some temperature index models. And then there has been some work in Canada on coupling MUSA with the SVS2 Crocus model with the SMRT radiative transfer scheme. So just to show you quickly the kind of filters that we have, this is just an example from the original paper. You see in green is the updated snow depth evolution from the various filters. The thing about filters, as Manuela said, they're only forward-looking, so you don't have any benefit of hindsight. So you only correct the current state, and there's no way to kind of correct the past. But for forecasting applications, these can be very useful. And what we're trying to show here is that the performance, of course, depends on the scheme that you use, and there's no universally best scheme. It depends on the problem that you have and how much computational resources you have. Smoothing is, I think, a more general approach, and this is helpful if you can afford to do smoothing, and if you do a kind of reanalysis, then you get this benefit of hindsight, and you get kind of a smoother solution, as the name also implies. But again, the scheme you should use is always kind of a compromise based on what assumptions you want to make and how much you can afford in terms of runtime. We also have the ability to assimilate different types of observations at the same time. This is often called joint data assimilation. So this is an example from the original paper where we assimilate LST data and fractional snow covered area data from MODIS at the same time. And these have kind of complementary information. So if you look in panel C there, you see that compared to the reference, which is just the model run without any updates, the SWE behavior is quite different, and hopefully then closer to the true SWE at the site. So most of the testing here is in the Spanish Pyrenees. And I'll continue with that as the theme for the second part here. So now we move on to this spatiality muse, and this is about spatiotemporal snow data assimilation. So what this means is that instead of doing the data assimilation independently for each grid cell or pixel in space, you allow the observations in different grid cells to influence one another. So basically you have information propagation in space as well as in time. And there has been previous work on this, especially with ensemble Kalman filters. And what we did was to extend this using these iterative ensemble Kalman methods that are less affected by this linearity assumption. And the reason we use the ensemble Kalman methods is that they are easier to localize, so they're easier to apply in this kind of spatio-temporal setting without them collapsing, which is a kind of a research problem at the moment with particle methods. So we've done this so far with drone data and with ISAT2 snow depth data, and then recently also LiDAR data in forests, and I'll quickly go through that. Just the key insight as to how this works is actually that you want to encode a correlation or dependence in your prior distribution. So your prior distribution is like your initial guess. So this could, for example, be the initial guess on the precipitation bias that Manuela talked about. And what I show here in kind of a toy model, this is in this paper in the appendix, is that if you have no prior correlation, then there's no way for an observation in an observed location, that's x1, to influence your model in an unobserved location, x2. But then if you just keep an eye on panel C, if you do add a correlation, then suddenly you're able to to update also in the unobserved location. And that's by this information bridge that occurs through the prior correlation. This is just a toy example, but we did actually do this with a real snow model and real snow data. So this is drone data from ISAS in the Pyrenees, and then we subsampled only less than 1% of the data in the catchment, and we assimilate this. These are just randomly selected points. And if you don't do any data assimilation, then you get the simulation there on the top right. And if you compare that to the observations, it's completely off. And then if you apply this spatiotemporal method where you consider the correlation in terms of just standard horizontal distance, then you get this kind of patterns. So it's a little bit better maybe, but you see this kind of blobs, and the predictions, you have quite some outliers in the scatter plot as well. So what we did, that's an extension of past work, is that we thought, okay, what matters for snow is not just typical distance, it's also topographic variables like topographic position index and slope and stuff like that. So we made a generalized distance that is a function of these things. And when we did that, the performance improved a lot. And then what improves things even more, of course, is if you encode snow depth itself into the distance. So if you use an earlier map from earlier in the winter, from January, that helps a lot then to predict the snow depth map in March. And that's what this final plot here shows. So we've been lucky to have Marco working hard on extending this to satellite data assimilation. So he had a paper published last year on ISAT-2 snow depth assimilation. And at the same time, he's also assimilating Sentinel-2 fractional snow covered area. Here he uses topographic position index and the meltout date from Sentinel-2 to create this distance. And what's really cool about this is that he's actually using snow depth information from ISAT that's completely outside of the catchment, because ISAT measures along these profiles, and no profile actually flew over the catchment itself. But thanks to the spatiotemporal methods, he's still able to update the snow depth and SWE within the catchment. This is a very busy plot, so sorry about that. But what I'm trying to show is that if you compare just the top row, if you do experiment C is only assimilating the snow cover, fractional snow covered area. Experiment D is assimilating only snow depth, and then experiment J is assimilating both at the same time. And you see that like overall, the joint assimilation works better both in the ablation and accumulation season. And you can see this more systematically if you look at what's called the CRPS. So this is kind of a generalization of absolute error. And if you look at then the red bars here, they tend to be lowest overall, both in the accumulation season and the ablation season. So this is quite encouraging, and we think there's a lot more potential to use this kind of sparse snow depth data for larger scale data assimilation. And Esteban also recently has a paper published where he showed how you can use the same approach to assimilate snow depth retrievals from a LiDAR, airborne LiDAR, in forest gaps to update the snow under the canopy. And he actually spent a lot of time on making this more scalable. So he ran this for, I think, 40,000 grid cells at 10-meter resolution, which is actually quite a large simulation. If you map that onto a 1 square kilometer grid cell instead, that would be roughly the size of Switzerland. So yeah, I think I'm still have a little bit more time. So I also want to talk about the recent preprint we have out, which is on this adaptive particle methods. So the idea here is that these particle methods are very popular in snow data assimilation because they have few assumptions, they're relatively easy to implement, and they have shown promising performance. But they can suffer from this collapse or degeneracy issue in higher dimensions, or if you have a lot of observations or very precise observations. And what we realized is that these methods implicitly rely on something called a proposal distribution. And based on the literature on what's called importance sampling, there are actually methods to improve this proposal distribution to make the methods more robust. And one of these is to adapt the proposal distribution. So that's what we suggest in this preprint I link at the top there. And this has also been applied to snow permafrost data assimilation recently. So one of the nice things about this is it also allows you to terminate the algorithm early. So in the case that the algorithm performs well already at the first iteration, it just reverts to the particle batch smoother. It's only for more challenging problems that it requires running more iterations. So this is the workflow, just like the standard particle batch smoother. You run a prior ensemble, and then you compute the likelihood, and you see how well each particle fits the observations. And then what you do is you calculate the effective sample size, which measures how much your ensemble has collapsed. If this is above some threshold, you say, great, we made it, and you can stop the algorithm. Otherwise, you use this kind of temporary posterior to generate a new proposal that you sample new particles from, and then you continue this loop until you get the threshold that you want. So if we compare it, this is an example again from ISA. So here we're just using a simple degree day model, and we have two parameters on the left, precipitation multiplier and a temperature correction. And the banana looking thing is kind of the truth. That's the Markov chain Monte Carlo solution. And if we use this PBS, we basically just get one particle with weight. That's this star. Because we have very precise observations. And if we use the ensemble smoother, which is a Kalman method, that's also slightly biased and underconfident, so that's not good either. If we use this iterative ensemble Kalman methods, they work a lot better, but they're actually quite expensive because you have to run many iterations. So that's what this shows. It's kind of zooming in on the truth, but it takes time, right? Because each time you do a new iteration, you have to run a new ensemble of model simulations. So with this ADA PBS method, we're actually able to match the performance of this iterative ensemble Kalman methods, but we have the advantage of having this early termination possibility. So here we could maybe have stopped already after 3 iterations instead of 4, and it relaxes this Gaussian assumption, which is a problem. Yeah, we also did comparisons to this Markov chain Monte Carlo method in terms of how the posterior distribution on parameters look. And both this adaptive particle batch smoother and this iterative ensemble Kalman method are kind of similar to Markov chain Monte Carlo, just that they require a lot less runs. The reason we don't use Markov chain Monte Carlo for snow data assimilation is it requires running the model maybe 10,000 or 100,000 times sequentially, which is completely prohibitive in spatial settings. We also tested this at some of the ESM SNOWMIP sites with the FSM2 model, and there too we're able to match the performance of the ESMDA, or this iterative ensemble Kalman method, at least most of the time. So I encourage you to look at the preprint if you're interested in any of this. Then the last thing I want to talk about, which I'm most excited about, is this idea of hierarchy. So here we're trying to use this thing called hierarchical Bayesian data assimilation. And what we're trying to do is to learn or infer these things called hyperparameters. So those are the parameters that control the parameters in your model. So that could, for example, be the mean that you set for your prior distribution, or the standard deviation that you set for your prior distribution, or maybe the observation error terms that you have to specify. Often we just assume these are known, or we set them to something vague, but this gives us a chance to actually infer these from the data themselves. And we've explored 2 ways in which this can be used. One is this climate-informed reanalysis, where we do this in time, and the other is in space, which is my colleague Greg has a preprint on, so I won't talk about that. I'll focus on the time aspect. We also have a recent paper published by Alouette van Hove that shows how you can use this to learn the observation error. So if you think about how you would set up a model run over many years, so here the Y are the observations and the N indexes different water years. You could either just assume your parameters are constant across all years. This is like a static calibration. That's not what we typically do in snow reanalysis. What we do instead is we say the parameters are constant within each water year, but they're allowed to vary across water years. This works really well if you have a lot of data in each water year, but if you don't have much data or no data at all, you'll just revert to the prior. So what we do instead is that we introduce this higher level of parameters called hyperparameters, and they build the information bridge across all the years. And this allows us to have this climate-informed approach to snow reanalysis. And the way it works is in this integral up there. And I'm happy to share the preprint when it's out, which is hopefully in a month or so. I don't have time to go into all the details. And this is an example of how it works. This doesn't really show anything yet because this is very zoomed out. This is again for Weissfluyok. But what we've done here is we've run these 3 different approaches. So static calibration, annual inference, and this climate-informed data assimilation at the bottom. And we turn off the data assimilation at the year 2000. we are assimilating SWE data. So if you zoom in, what we see, if you look after the year 2000, you see that the static calibration kind of does okay overall, whereas the annual inference, as expected, it just reverts to the prior. So it has a very underconfident prediction. Whereas this climate-informed approach, it's able to capture the observations with the kind of well-calibrated uncertainty. But then in the time when we actually assimilate data before the year 2000, this is basically equivalent to what we usually do. So we've kind of learned the patterns in the snowfall correction, which is the most uncertain parameter in this kind of approach. So this shows how that works in for 4 different snow sites on the left and for 4 different glaciers on the right. And we're doing the same thing here, but now this is in parameter space. And you see how this snowfall scaling that Manuela also talked about, how this varies a lot from year to year. But there is kind of a climatology of this parameter. So the blue shading shows how we're able to kind of infer this climatology after the year 2000. And this matches roughly with what we would get if we didn't turn off the data assimilation, which is the yellow line that you see. So the very last thing I want to talk about, this is a real word I found out. It doesn't sound like it, but it's about the future. And this is just like an outlook. So something I didn't talk about is that data assimilation and machine learning are highly complementary. And I think we could do more work on combining these two things. There's a nice reference there by Julia, who had a recent paper on this last year. I think we could also do more work on applying snow data assimilation in coupled systems, such as with other cryospheric components like permafrost and glaciers. And then there's been work now preparing for new missions like the TSMM. Yeah, I think we should really, I think that's already happening, but as a community, we have a really great opportunity now to start producing tailored global snow reanalyses, forecasts, and projections that are really using the information we know are helpful for snow models, as opposed to relying on atmospheric reanalyses. And I think this community developments and benchmarks, which we get through systems like Musa, can help a lot with this. And if you want to learn more about these things, I encourage you to stay tuned for an upcoming review paper led by Marianne Cowherd and Marco Mussolini. That's based on a workshop that we held last year. And I think this review paper should come out as a preprint sometime this year. So that's it for me. I'm sorry if I went a little bit over time. Here are the references, and I will link to the slides here as well. Thank you.
Perfect. No, right on time. Thank you so much, both of you. Wonderful presentation, lots of information. I see there are some questions in the chat, some of which have been answered already. So maybe feel free to just raise your hand and I can call on folks who have any questions. Questions, anyone? Sorry, maybe I'm not seeing raised hands.
Can I ask a question to Chris?
Yes.
Chris, when in your work on the spatial covariances, so you said like it's something that you do in filtering type of approaches, but were you able to actually apply that also in smoothing, like in the PBS or ensemble chem smoother? So where you have this, I think Marco's work, like where you actually have the spatial covariances or spatial structure. And I think I kind of like know how to do it in an ensemble chem smoother, but how do you do it in the batch smoother approach?
Yeah, so actually the work so far was always with the batch smoothers, but it was this ensemble common batch smoother approach. You could also do it with filters, but we wanted to have this benefit of hindsight because we were mostly focused on reanalysis type approach. So you have parameters that are static within a water year, and then you just run the whole simulation forward for that water year. And the key thing is really how you design this prior covariance on the parameters. And that's what Marco also has been working a lot on, improving ways to do that.
I should know that. Thank you.
Yeah, sure.
Great. Maybe I'll, I think there are a couple questions in the chat. I think this one was for one of your slides, Chris, from Ann Nolan. Let me just read it. Using data from forest gaps to estimate snow under the canopy can be problematic along an elevation gradient. At the lower elevation where the trees are warmer, the snow may be completely melted out during the canopy, under the canopy, but present in the gaps. At higher elevations where trees are colder, the snow melts out first and the gaps will last longer under the canopy because of shading. Any comments on that, Chris, just in terms of your assimilation of gap data to infer under canopy SWE?
Yeah, I mean I'm sure that's completely true, everything you're saying. Our work in a way was quite kind of empirical in that we just showed that the results that we get from the posterior by doing this are better than what we would get by not doing any data assimilation. But what's important to emphasize is that what we're actually correcting is not the snow depth or SWE directly. It's rather forcing parameters, for example, related to the snowfall bias and air temperature. And I know those two would vary under canopy and in clearings, but it at least seems to help. So there seems to be some information content there, but it can probably be improved a lot as well. Yeah.
Yeah, I guess thanks for that. And great talk, both of you. So you're comparing it to measurements that are made in a place that I presume is open, right? Not under the canopy. And so I'm always wondering, and I don't doubt, I mean, obviously what you're doing is really improving the estimates, but I always wonder, because we don't really make measurements under the canopy and in the forest, and it's so variable. And I know that just from spending a lot of time measuring snow in forests, it's like that's where we get it wrong. And so when we compare our methods with places where it's open, we always see like, hey, look, it worked. And then we don't go further to say, where did it not work? And I'm always interested in like if we had maps of where it didn't work, I'm guessing it would probably be in these forested areas, and that it would probably, the success of our methods would probably be somehow correlated with the density of the forest or maybe other forest structure parameters. So I know that, you know, comparing the data assimilation results with the observations, it shows an improvement, but I would love to see a map of like where it didn't work, and or just the degree of error across these forested regions. Thanks.
Yeah. So yeah, no, just to follow up. So we do actually have data under the canopy as well, just not everywhere, because the LiDAR is able, I think it is able to partly penetrate through canopy. And we do see exactly as you say that the performance is worse under the canopy than in the gaps, but the data assimilation nonetheless is able to improve the performance under the canopy as opposed to not having any data assimilation at all. That's what I was trying to say. But
Yeah,
yeah,
thank
we
you.
could
That's
probably learn
great.
a lot about why it's not working well, as
I
well as
appreciate it.
imitating. Yeah.
And you know, since we have LiDAR estimates of forest structure, density, height, et cetera, like it a priori before any snowfall, it would be interesting to see if we can incorporate those somewhat static maps to improve our estimates. Thanks.
Okay, there's one other question or a few. Let me ask this one. On the note of spatial structure, have you used snow models with any horizontal redistribution of snow? Does this affect the performance compared to a 1D snow model?
If that's for me, we haven't used any explicit redistribution modeling. I know there's a lot of work on that. Right now, all the redistribution is implicit in the snowfall correction that we do, which also kind of accounts for this in kind of a very implicit way, albeit. But I think if you add explicit redistribution, there will also be a lot of free parameters that you would somehow have to constrain in a similar way. But I imagine that that might be possible. I'm just not aware of anyone that's done that yet.
Yeah, I agree with Christoph as well. Like we don't use it, and yeah, I don't think that anyone has done that yet.
Okay, I see a hand raised. Zachariah.
Yeah, hi. I'm a postdoc at Oregon State, and I'm working with Snow Model and data assimilation within Snow Model. And Snow Model is a much simpler data assimilation approach than what you both talked about. And I guess I was curious if you had any opinions on how like simple data assimilation, if you know Snow Model works versus like compared to what you all are doing here.
I do want to try, Manuela, or?
I don't have strong opinions. I think that maybe there are some cases where maybe having a more simple data simulation approach works better than others. I think a lot of the work that specifically Christoph is doing is very detailed to understand, like methodologically, how data simulation methods can, improve things and where they might fail as in response to work. Simple methods might be more useful, like say for practical applications, like operational methods where you want to have something quick and simple that you can run. I don't know if that answers your question. With that in mind, I don't have much experience with the list and snow model data simulation system.
I think it's a direct insertion type approach or something like that, which can work really well if you have a lot of data. But if you don't have a lot of data, or you have more indirect data like FSCA data, then you can't use such a method. At least it won't work very well. So you need to use these kind of smoothers, or at least more sophisticated methods, I think.
Okay. Yeah, that was great. Thank you.
Okay, maybe I'll ask one final question, Chris. With frameworks like Musa, doing kind of continental scale or global applications, at least in the mountains, practically speaking, what kind of resolutions do you think we can tackle using some of these new methods that you've developed?
The work I've done, which is on very large scale reanalysis, I'm using like a temperature index type approach. So that's kind of a cheat because it's such a simple model. But I know Esteban has worked on a Mediterranean snow reanalysis using FSM with Musa, and that's around 1 kilometer resolution. So I think that's currently possible. I know you've also worked on Western US snow reanalysis at even higher resolution. So I think maybe the continental scale is reachable with, intermediate complexity models. Maybe even if we do something smart, you could go global too, if you have enough resources.
Great. Okay, any final questions? Okay, then there were questions about slides. So this is being recorded, so this will be posted with permission of the presenters. If they're willing to share the slides as PDFs, I can send those out to the mailing list as well. But the presentation has been recorded and will be posted to the SINTER website. So with that, let's thank our speakers for giving a couple of great talks, and be on the lookout for a future SINTER seminar kind of topic still being worked out, but we should be in touch soon. So thanks again, Manuela and Chris, for your time and effort. Really appreciate it.
Thank you for having